This is obviously ASMR. Have you ever wondered how the ancients wrote down their math? That's what we'll be exploring in this video. You probably know of Roman numerals. You've got, I'll grab a little piece of paper just for now. Let's see. There we go, nicely in frame. Alright. You probably know the Roman numerals. We've got 1, 2, 3. We've got 5. We've got 10. Maybe a little bit lesser known. We've got 50, 100, 500, 1000. But we'll be exploring that in another video. In this one, we're going to go even further back in time. We'll take a little trip to ancient Babylon, where the Babylonians lived. And the writing system they used was Cuneiform. What they did was they took a piece of clay. I've got some Play-Doh right here, but same purpose. They would have a piece of clay a bit larger than this, but this is all the Play-Doh I could find. And they would use a stick, kind of like this one. They would use a reed, but similar enough. But the important thing is that it has a rectangular ending, because these little angles is what really defines the writing style. You see, this is how they would write a 1. Right there. That's a 1 in Babylonian. Now, this is what you would call a wedge, and that's also where the word cuneiform comes from the Latin cuneus, which means wedge, and form, meaning shape. So, this writing form of writing would have been around since about 3400 BC. Could be slightly off, but it's an approximate number. And for example, the ancient Sumerians used it. But this numeral system that we're going to be talking about, that the Babylonians used, would have been in use probably from about 1800 BC. So, very old. It was in use for, cuneiform in general, as not a language, but a form of writing, was in use for a very long time, around 3,000 years, which is similar to how long ago it is for us that the ancient Romans would have been around. So, very, very ancient stuff. Alright, so this is how you write a 1. I hope it's a little bit visible. And very simply, you add 1 to get 2, 3, 4, 5, 6, 7, 8, 9. And there you have 9. Now, when they write 10, they do this. This is 10, and then you've got 11, 12, 13, 14, 15, 16, 17, 18, 19. And then when you move to 20, you would do something like this. 30 would be something like this. 40, 50. And then the interesting thing happens. So, what we see here so far is a simple additive system with a base of 10, non-positional. Just look at what you see and add it up, and that's the number you get. Similar to what the Romans had or the ancient Egyptians. But the ancient Babylonians were actually the first, that we know of, that thought of a place value system, a positional system. But it wasn't base 10 like we use. They had this additive sub-base of 10, but their true base was base 60, or sexagesimal, as we would say. So, if they wanted to write 60, they would do that. And that seems very funny, right? Because this is how you write 1. Well, you see, they didn't have any sign for 0. So you had to infer based on context whether this is meant to be a 1 or a 60. But when you write it like this, it becomes a little bit more clear. You get 1, 1, meaning 61. There's a 1 in the ones place. There's a 1 in the 60s place. So this is 61. And then if we put another 1 over here, can you guess what that means? 3,661. 3,661. There's a 1 in the ones place, a 1 in the 60s place, and a 1 in the 3,600th place, 60 times 60. Just like we would have a 1 in the 1 in the ones place, a 1 in the 10s place, and a 1 in the 10 times 10s place, or the hundreds place. Now, we already know that based on context, you need to infer which power of 60 we're talking about if we see a lone 1 somewhere. But what if you have this? Is this 61? Or is this 3,601? Well, for this situation, the Babylonians did have a solution, which was to put 2 diagonal wedges. These look a little bit too much like 10s. Excuse me for that. But something like this. And that would be a placeholder So this shows that there is nothing in between them. So this makes it clear that we're talking about 3,601 and not 61. They didn't use this in front. So for example, if you wanted to make it clear that this is 60, they didn't do this, which is strange, isn't it? Because this would make it a lot more clear than just basing on context whether we're talking about 1 or 60 or 3,600. But another interesting thing that they did was this can't only be 1 or 60 or higher powers. It can also be 1/60th, which was also pretty innovative. So not only can this mean 3,601, this could also mean, based on context, 60 and 1/60th. Okay, let's see. I made a few notes here. Did I forget to say anything so far? Okay, let's just write another number here. So let's write 3,721. Okay. Try to think with me here. So 3,600 plus, we need 120. So that's 2 times 60. And then 1. So this is 3,721. Okay, very nice. Okay. So, if this seems familiar, then that makes sense because we use this kind of system. Can you think where? It's of course our seconds, minutes, and hours. Well, not really hours, but the seconds fit into the minutes and the minutes fit into the hours. So, of course, we have 60 seconds in a minute, and 60 minutes in an hour. And that system of ours actually originates, well, not exactly, but it is based on the Babylonian numeral system, on their sexagesimal system. It was actually the Greek Hipparchus who made our hours and minutes and seconds the way they are now, which is another topic for another day, also very interesting. We'll be talking about calendars and time and how they came to be. But you'll have to subscribe if you want to hear more about that. Nice little plug. Don't usually do this, but it just felt natural there. Okay. Right, so Hipparchus actually originated the hours, minutes, and seconds that we know today, but he based the minutes and seconds being 60 on the Babylonians because he saw the value in it. And now you might be thinking, why 60? 10 seems like a far prettier number. Is that what you're thinking? Because then I would ask you, why 10? We generally have been raised with a decimal system, a base 10 system. But there is only one reason that we even use a base 10 system, and that's these guys. 10 fingers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That and only that is the reason we use base 10. And if that doesn't seem like a very good reason, it's because it isn't necessarily. And in fact, we'll be taking a look at the advantage of a sexagesimal system in just a bit. Firstly, maybe you're wondering now, oh yeah, it is easy to count to 10 on two hands. Wouldn't you lose that if you had a base 60 system? Well, first of all, of course we use smaller numbers more than we use larger numbers in everyday life. Whenever you're counting, when do you notice yourself counting higher than 10 on both hands? Probably not as often as you count to 10, or lower. And of course you keep that in a sexagesimal system. You can still use your fingers to count to 10, but another thing that you can do is count to 60 on both hands. And you might be wondering how. Well, that's because you can count to 12 on one hand and then use the other hand to count the number of 12s, and I'll show you how. You take your thumb of your whichever hand you prefer, and you simply count the segments of your fingers, because there are exactly 12 of them on the other fingers. If you take away your thumb, you have 4 fingers on your hand. And then each finger has 3 segments, which makes exactly 12. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then if we go beyond 12, we simply raise a finger on our other hand. So that's 112. So really we have 2 ways of saying 12. This is 12, but this is also 12. And then we go 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 60. And that's how you count to 60 on 2 hands. Of course, using both hands and this method, you could also count to 144 on both hands if you use the finger segments on both hands instead of raising fingers on one. But who needs to count to 144 on their hands? It starts becoming something that you would rarely use in daily life, but feel free to use this trick. This is likely how they did it in ancient Babylon. So now we know that that's not a downside to using 60 as a space. But what are the upsides? What are the advantages of sexagesimal? Well, for that, I'll have to illustrate a little bit with our trusty notepad. Alright, we've still got our Roman numerals up here, and I will try to illustrate. So, we're going to be talking about divisions and reciprocals. Namely, if we take our familiar base of 10, 10 has clean divisions into obviously 1, as does everything. You can divide 10 into 2, into 5, or obviously into 10. Now with 60, it's a little bit different. You can divide 60 into, of course, 1, but also 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, and of course 60. Now, you might be thinking, okay, sure, it has more clean divisions, but why does that matter? Well, I'll try to illustrate it with a little trick that you might be familiar with in our decimal system. So, let's see, what number are we going to use? Let's say you want to divide 7,363.4 over 5. So, I tried picking a number that's as hard as possible to divide by 5, even though, of course, if you know your arithmetic, dividing by 5 is never very hard, and that is kind of the point, because in our decimal system, working with any of these numbers is very easy, but I'll show you exactly why. You probably already have an intuition for that it is easy, but now you'll know why. So, when you divide by 5, I'm sure that you could figure it out just by seeing how many times 5 fits in 60, and into 300, and into 7,000, and then working out this part. And sure, you could do that with maybe in your head or with a long division, but there is a much simpler trick you might be aware of, which is simply to multiply this by 2 and then move the decimal point. So we'll do that now. This becomes 8, becomes 6, becomes 2, carry the 1, becomes 7, becomes 14, and then we move the decimal point. And this is this number divided by 5, and it was incredibly trivial without even requiring any thought to calculate. Now, the reason this works is because of reciprocals, because really, when you're dividing a number by 5, you're saying, and I'm going to make some math professors mad by the way I write this down, but I simply do not have enough space to write it all out. So, we're going to put it like this. Dividing by 5 is the same as multiplying multiplying by a fifth is the same as multiplying by 2/10, because 2/10 is the same as 1/5, right? If you divide 2 by 10, it's 1/5. 1 times 2, 5 times 2, numerator and denominator. So this is what a reciprocal does. And because we put our beloved 10 in the denominator, that's what makes it so easy to calculate with. Because if you're working with a certain base and you divide by that base, it simply moves the point, decimal point in this case. This is the same in binary, in hexadecimal, sexagesimal, in any place value system. That's why they're quite nice to work with. Now, conversely, if you wanted to multiply this number by 5, so 7,363.4 times 5. This is probably a little bit easier to calculate just because multiplying is usually easier than dividing, but we can use the same trick here. It's the same as multiplying by 10/2. So we can divide this by 2 in this case. So we get 3,005. This becomes 1, so that's 6. This becomes 5, that's 3, so that's 8. This is 1. And then 7. And there we go. That's our number. So we've got 36,817. And in this case, it might not have saved us as much time. Maybe it would have cost us about the same to say, okay, 0.4 times 5 is 2, 3 times 5 is 15, 5 times 6 is 300. Would have probably been around the same time, actually. But the point is that we only really have 2 and 5 as easy numbers to work with, along with 10 and 1, of course, in our decimal system. But in sexagesimal, we have a lot more numbers. And in the same way that 2/10 is the reciprocal of 5, we have reciprocals here. For example, between 6 and 10, 5 and 12, 4 and 15, 3 and 20, 2 and 30, and 1 and 60, of course. And now we're going to use that. So we're going to go back to Cuneiform, and we're going to do a little calculation, a little arithmetic on clay with our cuneiform writing. All right. Let me hold it like this. Okay. So what we'll do to stay sane, I will refer to the places as seconds, minutes, and hours, just to make it clear what I'm talking about and to keep it a little bit more clear for myself. And then if we move into the position next to that, so if we have 4 positions here, then I would say in this case 1 hour, 2 minutes, 1 second, and 1/60th of a second. Alright? Okay. So the calculation that we're going to do, I'll try to make it a little bit tricky, just to show how convenient Cuneiform and the Babylonian numeral system can be. So what we'll do is, let's see, we'll say 7 hours. 1, 2, 3, 4, 5, 6, 7. Let's say 11 minutes. 11 minutes. And let's say 3 seconds. And we're going to divide this by 12. So, divided by 12. I don't know if they had any kind of way to write down that you divided. So, you'll just have to remember that this is what we're dividing by, okay? So, since we're dividing by 12, that means we can multiply this by 4 and then move the sexagesimal point, not decimal point in this case, the sexagesimal point, to divide 7 hours, 11 minutes, and 3 seconds by 12. We'll be multiplying this by 5 and then moving the sexagesimal place. So dividing by 60. Because 5 times 12 is 60, of course. It is the reciprocal. So first we'll multiply 3 by 5, which is 15. So I'll put 15 right here. There we go. And we'll multiply 11 by 5, which is 55, which doesn't quite hit 60, so we don't need to carry anything to the next side. So we have 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5, and then 7 times 5 is 35, of course. So I've got 1, 2, 3, 1, 2, 3, 4, 5. And then we've got 35 minutes, because we're moving the sexagesimal place. We've got 35 minutes, 55 seconds, and 15/60ths of a second, which is 1/4 of a second. Pretty easy, right? Now, for a comparison, I'd like to do the same calculation on paper. So again, what we did, we had 7 hours, 11 minutes, and 3 seconds over 12. And then what we do is simply 15, 55, 35, and then I'll use a semicolon to denote that we're moving into the fractions. Do you see how fast that is? And we can do this with our time, our at seconds. We have the benefit of our sexagesimal system there, and that's something that Hipparchus knew. And that is why he chose the Babylonian sexagesimal system instead of choosing some strange, inconvenient system like decimal, base 10. So, to show you how much longer this calculation would take, in base 10, I'll do a little long division. Actually, first, I'll have to quickly calculate how many seconds this actually is, which, let's see, that's 7 times 3,600 is 21, that's 25. 25,200, and then we've got 11 times 60, which is 663. So that's 25,863. Okay. And then just to check the answer here, we've got 35 times 60. Which is, let's see, that's 1,800, and we've got 300, so that's 2,100, plus 55, plus 1/4. So 2,155, comma, 25, okay, or, sorry, 0.25, comma is what we do in the Netherlands. Okay, so now that we know the numbers, the decimal numbers we'll need to use, let's do a little long division. So we've got 25,863. All right. So I'll put 12 over here. 25,863 over there. And we'll do it like this. Now we can see 24 fits in there. One left, move the 8 over there. This is 2. Here we fit 12, so that's a 1. We have 6 left. 6 moves here. We can take 60 out of that, which is 5. Leave 6 here. We put the 3 over there. 60 fits in there. Put a 5 here. Got a 3 left. Put a 30 there. We've got 24, which is 2 again. Now we've got 6, 60. Nothing left, and that's 5. And we can see that, long division is a very efficient way of division, but it takes a lot more writing down and a lot more steps where you could potentially make a mistake. And just in general, it definitely took longer than using the reciprocal. So the message is that even though decimal is not too bad, you get even more easy calculations when you use 60. Now you might be wondering, is everything about sexagesimal so good then? And I've got one thing that would be a little bit annoying, because in our decimal system, you probably remember that in middle school you had to learn the tables. So you would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, you had to memorize all of these, but some of them are very easy, right? For example, we can already cross out all of the ones, because that's just the number itself. We can cross out all of the tens. Because that's just the number itself with a 0 after it. We can also make a little diagonal line and cross out this entire part, because that's just duplicates. So the numbers on the line you do actually still need to know. I was a little bit too enthusiastic with that. So we'll put those on there. 6. We've got 49. 64. We've got 81. So these numbers, and then whatever goes in there, right? So for example, for 2, we got 4, 6, 8, 10, 12, 14, 16, 18, and then 20. And for example, for 5, we've got 25, 30, 35, 40, 45, and below that we've got 20, 15, 10. Those are already very easy, right? And then even the 4 has a pattern to it. We have 4, 8, 12, 16, 20, and then it repeats. 24, 28, 32, 36. We've got 4, 8, 2, 6, 4, 8, 2, 6. So there's plenty of these patterns you can find. Even for 8, we've got a pattern. We've got 8, 16, 24, 32, 40, 48, 56, 64, 72. The reason that 4 and 8 have a pattern is because they are multiples of one of the clean divisions of 10. So we've already got relatively easy tables here. Now I'm showing you this not because I don't think you know, but to illustrate that with the sexagesimal system, what do you think this is like? Because in the sexagesimal system, we've technically got 60 times 60. That's our table. Now, of course, we can already cross out the 1 and the 10 like we did before, but that would still be 58 times 58, which is 3,364, if I'm not mistaken. And then, of course, we can roughly divide this by 2, because half of it is duplicate. So we've got 1,682 different products to memorize. Now, of course, because 60 has more clean divisions, many of these will have nice patterns, like, for example, the 5 or the 2 in this system. But there's still a lot of numbers in there that would not be very fun to memorize. Then again, you don't necessarily need to. In our base 10 system, it's just very easy to do it. Even middle schoolers can do it. In the base 60 system, even though it would probably be feasible for a human to memorize these tables as well, you don't necessarily need to. If you know a lot of them, for example, if you know up to a certain amount of tables and then the rest you have to look up, it's also not necessarily a problem. Especially in the time before calculators, when you had to do all math manually, you would probably benefit from having an easier overall system like this, while sometimes having to look up a number, rather than using, for example, base 10 and having more manual effort in the calculation itself. Now, I think we're getting to a point where I've said most that I know about this writing system, but let's erase this. The nice thing of working with clay is that you can just use your fingers to erase it. At least it takes a little to really get rid of it. It takes a little patience, but we're getting there. And then we'll do one final calculation. In the Babylonian numeral system. Okay, so let's think of a tricky one this time. All right. Let's say let's say 27 hours, 41 minutes and 53 seconds. $27 hours, 41 minutes, and 53 seconds. Let's divide that by 15. So we know that 15 fits in 60 4 times. So we multiply this by 4 and move the sexagesimal place, sexagesimal point. So let's start multiplying. We've got 53 here. 53 times 4 is 212. 212, the biggest that 60 fits in there is 180, which is 3 times 60, so we carry the 3 already. And then we've got 82. 212 is 32. So this becomes 32. Multiply this by 4, which is 41. So that's 164. 164. 60 fits in there twice, so we carry the 2. And then we've got 44. So we add 4 to this. And then that's a 40. And then we have 27 times 4. We've got 7 times 4 is 28. So we've got 108. 108, so we carry the 1. And then we've got 48 left. So 48, but we carried 2 here, so we got 50. So we actually need to erase those. Not the 10 here though. And this becomes 50. So 1, 2, 3, 4, 5. And that gives us, moving the sexagesimal place, of course, gives us 1 hour, 50 minutes, 47 seconds, and 32 sixtieths of a second. That's what? 27 hours, 41 minutes, and 53 seconds divided by 15 is 1 hour, 50 minutes, 47 seconds, and 32 sixtieths of a second. Now, because I did the erasing before this, I do think my writing could have been a little bit cleaner. I admit that. But I hope that I showed you the beauty of Cuneiform and the Babylonian numeral system, the advantages of Sexagesimal, and I hope you had fun. I hope you relaxed a little bit. And yeah, doesn't it look pretty? I can tell that I kind of erased what was on this side by holding it there. So, thank you for watching. Let me know if you like this type of video. I thought it was really fun to make, actually. I'd love to. I'm honestly really hoping that you guys like this kind of stuff, because honestly, I really do. So I would love to make more like this. There's lots of nerdy stuff that I'd love to talk about, like the history of calendars and ancient writing systems, the Egyptian numeral system, Roman numerals, that kind of stuff. It's all very interesting because it all has so much influence on the way we do things today. That's how I started looking into this kind of stuff. It all evolved from here. So, I hope that you find it as interesting as I do, and yeah, I hope you'll see me in the next video.